Hi there, this video is going to talk about the effects of solubility, or how we can change solubility. The first one is the common ion effect. This one is using Le Chatelier's principle to change how much is actually dissolved. So let's say I've got this system going on right here, where I've got a solid barium sulfate. It's not very soluble. Some of them are making ions. My KSP is relatively low. So let's say I want to make it more soluble. If I want more of this solid to actually dissolve, I can do so by maybe, let's remove this. If I remove these ions, then suddenly this product side over here has too few of ions. So thus it'll have to proceed to remake some of those ions. A different way I could do it, if I wanted to make it less soluble, in other words, I wanted to make more solid, then I'll have to put in more of the ions. If I add more ions, like let's say I'll add H2SO4, that's an acid, what I'm really adding there is H pluses and SO4 ions. So suddenly if I add more SO4 ions, then this product, there are too many of these, my Q is greater than my K, so it'll have to proceed to remake equilibrium. In other words, it'll proceed to make more reactants in that case. Thus I will get more solid. So let's take a look at the math part of this whole shifting that was happening in Le Chatelier's principle. I'm going to calculate the molar solubility of CaF2. That's that term again, at 25 degrees Celsius in a solution that's this time 0.01 molar calcium nitrate. So here we go. The first thing I should do is write my KSP expression. And this is going to be a situation where I've got like an ice table going on actually. So I've got CaF2. That's what I want to find the molar solubility of, which means this is the KSP for it. And it's going to separate into Ca ions and two F1 minus ions. Those are my two aqueous parts. Now if I were to write the KSP for this, it's going to be calcium and my fluorine, and it's going to be a 2 squared part for that, since there's a 2 in my coefficient here. Now like I said, this is the solid, and these are my aqueous parts. And I do have an ice table situation here, because I have added something to this whole bucket. So let's take a look at the ice table. This is a solid, and it's not in my KSP expression, so I don't need any numbers in this laid. That's not important at all. And then I'm looking at, initially everything is at equilibrium. So I've got X and 2X amount of this. And then it is in this solution. So it's kind of like they had equilibrium, and then we added calcium nitrate. I know that's not exactly what it says, but that's the kind of idea that's happening here. So if I have everything in equilibrium and I add something else, it's going to shift it one way or the other. Or even if I have things, I'm going to make it into a solution that happens to have more ions, that creates that shift also. So suddenly I'm going to be adding, here is calcium, the common ion. Nitrate isn't affecting the KSP at all, so I don't want to include that information anywhere. But the calcium, I've added plus 0.010 molar of that. Now we do need to be careful, because if you notice, if I had something that was a common ion with nitrate, the nitrate has a 2 here. So this is actually 0.02 molar of nitrate. So that's just a tricky thing that could be in future problems. It's not in this one, since we have a 1-to-1 ratio of the calcium, but it could be trickier if you had to do the nitrate part. So keep that in mind. And I'm not adding anything for the change for fluorine. I haven't added any extra ions of those. So now if I add it up, I've got X plus 0.01, and this lane will be 2X. So now I'm going to plug that into my KSP expression. My KSP is 3.9 times 10 to the negative 11, and that equals X plus 0.01 and 2X squared. Well, I can see where I'm headed here. I'm headed down quadratic equation land, and we know all chemists would hate to do that. That's too much work. So right here, if I can solve for this problem here, I won't have quadratic equations. An AP test is not going to have quadratic equations. Even if they did, it'd be a calculator one, you'd use your calculator. But they won't, so don't worry about it. So I'm going to assume right here that that 0.01 is definitely greater than the X. And if you think about it, if my KSP is 10 to the negative 11, anything that I come up on with the calcium and fluorine have to be really, really small numbers. It'll be much, much less than that 0.01. So this is a pretty safe assumption. So suddenly this becomes 3.9, 10 to the negative 11 equals 0.01 times 2x squared. I'll simplify that to 4x squared. And now I can solve for x. And I got 3.12 times 10 to the negative 5. That's my molar solubility, because that's my X part, and I called X my calcium, and my calcium is a 1-to-1 ratio with calcium fluoride. So that is my answer. What's the molar solubility? This one right here. If we take a look at this number and the problem you did before, this problem here, we calculated the molar solubility when it wasn't in calcium nitrate, and we got 2.1, 10 to the negative 4 on that one. And now, looking back here, oh man, where'd it go? Here we go. Before we got 2.1 times 10 to the negative 4. That was the molar solubility when I hadn't added any common ion. And now I got 3.12, 10 to the negative 5. I can see it's a lot smaller, or at least a tenfold smaller. 10 to the negative 5, 10 to the negative 4. So that does show that if you add a common ion, it will cause more ions to be able to shift it towards to make more solids. So that's what that was happening here. I added more calcium. It shifted or proceeded to make more of your solid reactants. So it's less soluble when you have it in a common ion. Well, that was how to make things less soluble, in other words, to create more of a solid. What if I wanted to make it more soluble, which is the first thing I kind of talked about. So there we want to use something like complex ions. So take a look at the different values we've got here. So I've got the KSP of AgCl. Here I wrote it out down here. So that means 10 to the negative 10. I do not have a lot of ions. Very few of these ions are happening. So I've got a lot of solid. So what if I wanted to make AgCl more soluble? In other words, I wanted to create the solids to dissolve easier, right? Well, in order to do that, I've got to somehow shift this equilibrium. So I'm going to use Le Chatelier's principle to make that happen. And to do that, I'm going to use something like complex ions. Take a look at these values. This is called Kf. This is when we make these complex ions, which you saw when you did the iron thiocyanate lab, FeSCN. That was the one you did the Kc of FeSCN. You made a complex ion. Maybe you didn't even notice it. But this is a common complex ion. It's here at the top here. And my Kf is 1.7 10 to the 7th. That's a positive value. You've seen that before on the BA-EDTA problem. That tricky AP question that just kind of gets you. We got to know about. But look at all these numbers. They're all really big numbers. 10 to the 42. I mean, really, have you seen that before? No. What that means is they really like to make the ions. My Kf here, they call it Kf because they're forming a complex ion. Kf forming. It's 1.7 10 to the 7th. That's like a freakishly big number. Not as much as 42, but it's a very big number. Which means it really wants to go to the products. So here's what I'm going to do. I'm going to make this AgCl and put it into ammonia, NH3. What happens is then the Ag will hook up with the NH3 and make this complex ion. It'll force the Ag to be lost and made into these guys. Once the Ag is in the form of this complex ion, NH3, it's now like you've lost it in this equation at all. So it's like there's zero of it. Well, equilibrium can't have that happen. It's got to proceed to make more of that. And when it does that, a lot of the solid is going to dissolve. So you can keep adding NH3 in order to force the solid to all dissolve. And that's one way that we can dissolve solids that otherwise would not want to be dissolved, using these complex ions. So the name of this game is to look at the different K values that you have, the values of them in magnitude. Like that's super big, so it's going to happen. This number is very small, so it doesn't like to happen. If you want to make something happen that doesn't like to happen, well, make it tricky and make them force one way or the other, what they would not prefer. Like us taking away the silver by making it to NH3, and that'll force AgCl to be more soluble.